Welcome everybody to the November 2025 meeting of the Mornington Peninsula Astronomical Society. And as usual, I'll look at a couple of things here that have occurred in the last month. And if you look at the middle top, you'll see Nerida's one that she caught on her smartphone, her Samsung, on the night of the 12th of November here at the Briars. And you can see the nice fingers of light pointing up from the aurora, and by the looks of it, she was probably down where the members' entrance is, down the bottom there, because she's missed the trees on the right-hand side. As you see, that time lapse there shows it coming and going very, very well. Over on the right-hand side, we'll sort of show some smoking hot debris. This was found on October the 18th at near a mine site about 30 kilometres from Newman in northern Western Australia. And I had to show this because this was the police footage from their body camera, and they're all decked up as if this is some nuclear disaster. If you turn that one off, it won't appear on YouTube, so you might want to turn the middle light back on. Yep. Yeah. So apparently it was it was smouldering and on fire when it came down as well. And you're quite, particularly looking at them there, you quite anticipated something like a Sigourney Weaver xenomorph to leap out of the thing and wrap itself around that policeman's head, just to give it some credit. Now, I don't think they've still completely confirmed what it is, but they believe it to be a part of a Chinese rocket. From the fourth stage of it, although they're still looking at that. And ultimately it's China's responsibility to come and clean it up and take it away. Down in the bottom left-hand side there, if you recall several years ago, the first exoplanet, in other words a planet around another star other than our Sun, 51 Pegasi b, was detected. We've now gone over the 6,000 exoplanet mark that they've confirmed, and there are actually I think about 1,000 others that they're still working on confirming that they've detected, but they're not quite there yet to sort of say it. Now, of that 6,000 odd, only about 200 are terrestrial planets, and terrestrial planets are defined as ones that might be like Earth, Mars, Mercury or Venus. So in other words, rocky small worlds. So only a fairly small percentage of them. I think the biggest percentage are ones about the size of Neptune or Uranus. Middle bottom there we see Comet C 2025 K1 Atlas, and since we last met, that broke into three pieces. Shown there is the image that was taken from an observatory in Italy at the time, which shows two, and there was a subsequent one taken on a public domain telescope that actually shows three very, very clearly. So in other words, it came too close to the Sun, the Sun's gravity pulled it apart, so it wasn't bound together very, very tightly. So you're not going to see that brighten up very much more now. And lastly, down in the bottom right-hand side there, we see a veterinarian from South Australia who was driving along on his Tesla car along the Augusta Highway in South Australia near Port Pirie. And unfortunately for him, something hit his windscreen and he's pointing to it. and it was thought to be a meteorite, but they're still looking into whether it could be something else, because they were claiming, certainly on the news report, that it had partly melted the windscreen, which would be very, very unusual for a meteorite, because usually they're cool by the time they reach the ground, because they're only in the atmosphere a small time. Even though the surface and in front of them, if they're coming in, gets very, very hot, there's not enough time that they're up there to actually conduct through to the entire body of it. So they're still not sure that it's a meteorite, but if it is, it's highly unusual, because it's quite rare to get a meteorite come through a moving vehicle. They claimed actually on the news report on ABC that this would be a world first, but it has actually happened at least once before. In a German autobahn, the lady was hit with a meteorite coming through the windscreen and bouncing off her steering wheel, which likely saved her. Yes, Fred?
Is this business, is this becoming a more regular occurrence, they're getting things out of the sky, or is it just a one-off?
Well, if it's a meteorite, then pretty much you're incredibly low odds of it occurring, and particularly in a moving vehicle as well, because you know, you just need to be a metre or so away from it, and you'd never know that it came down. In terms of space junk, though, there's more space junk up there, so you think there's going to be more likelihood of there being issues of bits and pieces coming down. So over time, if there's more up there, you're more likely to get it coming down.
Get to the bottom of it.
Oh, the big lump on the top right there, and others like it. I'm sure they will get to the bottom of it, but they can't enforce it, is the problem, because there's no law up there. It's all done on a goodwill basis. Right, so lots of things falling from the sky and happening in the sky. So tonight, welcome to the Mornington Astronomical Society, and I'll read out the new members since we've last met. There's Amy Collison, Ray and Dwayne Annabel, Ebony Tomlins, Jacob Gribble, Malcolm and Margaret DeBono, and Jennifer Quinlan and Jack Wines. And I don't think any of them are here tonight, so we'll welcome those to the Society. I'll quickly go through the events of the past and coming months, then I'll throw over to Chris for Astromofo. Guido's not here tonight, but we'll include Sky for the month when this goes up on YouTube. He's working on it over the weekend. Then John Goodall has offered to talk about astrophotography with film. So we're taking a step back to last century, in fact a millennium ago, and he'll reminisce some of the things about film. Then we'll look at the meaning of space-time, given by Professor Juan Maldacena, who gave a public lecture at the Perimeter Institute on that. We'll look briefly at how the human body handles artificial gravity, for those of you who remember things like 2001: A Space Odyssey, with the space station that rotated to produce artificial gravity. NASA indeed looked into that. And then we'll close with the Escapade mission to Mars, which was launched only less than a week ago now. And we'll explain a little bit about that one, and we'll actually close with the launch of it from Cape Canaveral. So recent events, we've had a few. Picture in the background was a visit on, when was that, 9th of November, on a Sunday here at the Briars. Melbourne University Physics Department sent some of its PhD and MSc students down here, and we're looking at potential collaboration with them on doing various things with their theses. On the 16th of October we had Yarra Valley Grammar here, and we had a good turnout there, unfortunately under complete cloud. We've had them here at least once or twice before in the past as well. A couple of days later was the working bee, then the committee meeting, and the committee meeting for that month just really was focused more on the lease and on the events calendar. And John Goodall was kind enough to pull this out of the local newspaper today, and it says the new lease approved for the Astronomical Society. So yeah, Chris got his photo there next to a telescope and the lease. What it really means is it's gone through council and it's now gone to a month of public consultation to see who keeps quiet and who whinges too much.
How long is the lease or hoping to lease it?
3 by 5 years.
Yeah.
So
Yeah.
15 years. We're looking to get secured over here, which gives us pretty good scope to do a lot of stuff with the site.
Yeah, that'll be
So
fantastic.
Fred, this isn't something to complain about. Just
So 15 years, we could have a lot of potholes in that time.
Oh, them will get fixed when they don't like it, all right, because I told them last night.
Maybe it'll be a month and a half.
On the 24th of October, we cancelled the quarterly Skag night because we didn't have any bookings for that one, so we had a night off on that. 5th of November was St Michael's Primary here at the Briars. They had good cloud conditions and they really enjoyed themselves that night. A couple of days later, there was a public night where Trevor gave the talk, and it was pretty cloudy, but there was at least something to be seen. 13th of November, Trevor, who's not here tonight, went out to the Victorian High School Science Lab Technicians Conference and spoke to them about meteorites and that, and flew the MPAS flags. And they seemed to enjoy that. I think he talked to them over 2 days, so he must have given the talk a couple of times. 14th of November, the next day, we had the Indigenous Astronomy Night here with Tim Patson. Cloud probably kept some away, but it nevertheless was quite good attendance, 77 there. And 15th of November, we had the secret handshakes of the Freemasons from the Gregorius Lodge in Melbourne come down to the Briars. And yes, they do have a secret handshake, but I can't tell you what it was now. And they had 25% cloud, and they appear to enjoy it, and I think they want to come back next year sometime as well when the weather's a bit warmer and there are other things in the sky to see. Coming up soon, we've got a few things, given that this meeting is not held in December, so this is the last one for 2025, and the next one will be in January, on the 3rd Wednesday of January. So this coming Saturday, we've got the Working Bee members barbecue here at the Briars, followed by a committee meeting by Zoom next Wednesday, and then next Friday, as in not the coming Friday, but the one afterwards, we've got 3 cub groups organised together, Carrum Downs, Seaford and Langwarrin, coming here to the Briars. And there's about 50 cubs for that one. Next Cosmology Discovery group will be here the next day on the Saturday at the usual time on the Saturday afternoon. 5th of December was public stargazing, or will be public stargazing at the Briars. Trevor will give that talk, and we've been booked out on that one for quite a few months already. 6th of December, we've got the Christmas concert here at the Briars, and we could certainly do with some more people attending. At the moment, we've only got 34 bookings for that one. So time is running out on that. Christmas dinner is the following Saturday after that, 13th of December, and you have to book for that one. And so far we've only got 42 members booked for the dinner as well. So again, that is also low. So it may be a sign of the times that people are financially struggling possibly to come along to this, even though, for example, the dinner is done at cost or even under cost for members. 2nd of January and 3rd of January, which is the first Friday and Saturday of 2026, we've got public stargazing here at the Briars, and they're filling up there already. The first one's already fully booked, and the others are going gangbusters at the moment. And 16th of January, we're going to have a visitor here from an observatory in Calgary.
All right, welcome to AstroMofo number 28, globular clusters, and this is the last one for the year. So this is a bit loud, isn't it? So this is the last challenge, and members were tasked with getting photos of globular clusters. So I thought I'd start off with one of the biggest ones in the sky, 47 Tucanae, which is nice and high at the moment, right next to the Small Magellanic Cloud. And this one was with a 200 mil Newtonian and a light pollution filter on my Astro camera, and just from home this one was. Okay, people who completed this one were Fred Prater, Michelle Sykes, Mark Stevens and myself, and we've got another 47 Tucano here by Mark with his C-Star. Good job. So 47 Tucano or 47 Tuc or NGC 104 is about 16,700 light years away, and it appears, like I said before, it's right next to the Small Magellanic Cloud, and it contains, estimates are at around about 1 million stars. It's about 120 light years diameter, and if you compare that to 120 light year diameter space around the Earth, we only have about 640 stars in that sort of volume of space. So if you can imagine, instead of 640 stars around us, imagine about 1 million of them. It would make for a pretty bright sky. You wouldn't really be able to get views of much else. So it'd be daylight all the time, I reckon. Now what have we got? Hang on. This is another one by me. NGC 362. So this is also in Tucano. This is 47 Tucano's lesser known cousin. It's also right next to the Small Magellanic Cloud as well. And it's around about 29,000 light years away. So it's about roughly twice as far as 47 Tucano. But it's also really nice to look at through a telescope as well. So I know that 47 Tucano gets all the attention when we do our public viewing nights, but this one is also quite a nice one to point a telescope at, and even with a 200mm Newtonian, I've had a pretty decent look at it. So it's another one not to be forgotten, and that's around about...
Did you really do 120 seconds?
120 seconds, yeah, with a light pollution filter.
Is that necessary?
With a light pollution filter, it does tend to reduce the amount of light coming through. So it does dim them down a little bit, and I found that I was still able to get, it wasn't overexposing the image with that. So the 294 that I use, ASI 294, has got a decent well depth too. So to compare that is pretty much a full sensor view of it, and that's the zoom in on the right hand side, but that's a full sensor image of it. And if you compare that to that is also pretty close to a full sensor view. So that is the relative size between 47 Tucano and 75. So they're quite different in size when you look at them. And okay, these ones were sent in by Fred Prada as well, with taken with the Celestron Origin Smart Scope. But I'd never actually heard of these, but you can probably think of it as a C-Star on steroids. It's a really nice 6-inch Rasa telescope on a robotic mount, and pretty much works with a phone app as well, and you're able to get some really nice shots with it. So M22, M55, NGC 6541, 6752, 22, 75, 6391. So what we've got here, M22 is in Sagittarius, and that's around about 9,700 light years away. M55 is also known as the Summer Rose Star. It's also in Sagittarius. That's around 17,000 light years away. M75 also in Sagittarius, down the bottom there, and that's quite small, but that's quite some way out. That's 67,000 light years away, approximately. These are all from NASA and Wikipedia, these distances. NGC 6541 has an interesting name. It's called the Cacciatore Cluster. And that's in Corona Australis, about 22,000 light years away. 6397 is in Ara, and 6752 is in Parvo. So a lot of them are in the southern skies: Parvo, Ara, Corona Australis. So these are all, pretty nice targets, and nice shots of them there as well.
Those were all like 10 seconds.
Yeah.
Two.
Yeah. About how many exposures did you?
Not that many.
Not that many? Yeah.
Maybe because it's F2.
It is F2. Yeah. The Newtonian is F5, but I'm not sure is there any filters on this? No. Yeah. The tri-band filter does cut out a fair bit of the light. You can see it in the histograms when you're imaging. And M22, a really nice one of M22. So we've got the two shots here. The left one, like Fred's got there is with an ASCAR telescope, 600mm focal length, and the one on the right with the Celestron origin. So thanks very much, Fred. A couple by Michelle Sykes. So well done, Michelle, with the C star. We've got C106. C106 is also known as 47 Tucanae as well. So that's another name, and the C is from the Caldwell catalogue. Caldwell catalogue is just another catalogue of objects compiled by Sir Patrick Moore, an English amateur astronomer, and he created this catalogue in the 1980s, sort of to complement and supplement the Messier catalogue. So it's, how many objects has he got in it?
109.
There's 109 Caldwell objects. Thanks, Greg. And yeah, Sir Patrick Moore was also a presenter of BBC's Sky at Night for about 40 years as well, so did quite a bit.
Well, is his middle name.
That's right, yeah. Or I think I'm not sure if it's his middle name. It's an old family name.
It's on his mother's side.
Yeah. Okay, so C106 was 47 Tucanae, and M2 there is in Aquarius, around about 39,000 light years away. Couple more by Michelle there, M30, and what's the other one? 6723. 6723 is an interesting one because it's right next to the reflection nebula there in the dark nebula in Corona Australis, sometimes called the Anteater Nebula. But the M30 is also known as the jellyfish cluster. Not sure if I see a jellyfish there, but and that's around 27,000 light years away. And NGC 6723 is known as the chandelier cluster. So all these objects, you notice, they're all pretty far away. They're not generally in our Milky Way, but they generally orbit around it. Some of them may have been formed with the Milky Way, and others may have been captured along the way during mergers with other galaxies, because some of them have retrograde orbits and not orbiting the same way. They're orbiting in reverse around the Milky Way. And generally they were formed from collapses of what's called giant molecular clouds. So these were formed, globular clusters formed very early on in the universe. It's probably around the same time as galaxies were being formed. And you get these giant molecular clouds which collapse under gravity, and then just create this burst of star formation, and all these stars get born pretty much at the same time. Although they are finding multiple populations in these at the moment, and there was a really good talk at Vastrock when we had Vastrock here. Madeline McKenzie did a talk, and I tried to find it on our YouTube, but it's gone. I couldn't find the Vastrock talks.
Should be there.
Okay, we'll have another look. But if we get them up, I'll put a link to it because it is a really interesting talk on globular clusters. Okay, these ones are by me, M75 and M79. These are crops. So M75, Fred had a photo of that earlier, and M79 is in Lepus, the hare. And that's just above Orion, so just above the Orion constellation. These are pretty nice visual objects to have a look at. And 3201 and 6752. 3201 is also Caldwell 79, and that's in the Vela constellation. And this, I had to get an image of that fairly early because Vela is still quite low in the sky. Had to wait till a little bit later on. So this was at around about 4 a.m. That I'd set the scope. I wasn't up at that time. It was just automated to get that. And 6752 is also called the starfish or the windmill cluster. And I wasn't quite getting it, but you do sort of see it's got a little bit like tendrils coming out on it in some way. So that's the starfish or the windmill. Okay, now this challenge saw us image 13 different targets in total, so 13 different globular clusters, so well done, gang. And there's the list of them there. And a lot of these are actually not just photographic targets, but also visual targets to have a look through a telescope at. So if you want to take note of the list, which I'll put up on the socials later, you can also try and find these visually through a scope as well. Not all of them, but the brighter ones most certainly you can. And this being the last MOFO challenge for the year. This is the list of everyone who contributed to the MOFO challenge this year. So really good job, everyone. We had about 39 contributors, and between all of us, we completed 79 challenges. So multiple ones by some, single ones by others, but in total 79 challenges completed, and there was hundreds of images as well. So really good job by everyone, and hopefully next year we'll get some more. And don't forget your calendar. Happy holidays, everyone.
Thank you, Chris, for doing all that.
Thank you. Appreciate your contributions as well. Any questions? No. Thank you.
A break for a month. So there's no need.
2 months. Yep. I get a break.
Even though we're not doing it.
What?
Do we have a target for next month even though we're not doing it?
No. It's free reign. Whatever you want to image. Orion.
All right, welcome to Sky for the Month for November, December and January. So this is the photo from the November 2025 edition of Narrator's article in the Morning Peninsula magazine. And thanks very much for picking my photo of Comet C 2025 R2 Swan for this cover image here. So let's look at the solar system first. This is the view from the top on the 19th of November, so just a few days ago. So here's a view of the inner solar system on the 19th of November. We can see that from our point of view on Earth, all of the inner planets are very close to the sun, right? We have Mercury basically directly between us and the sun, Venus hiding almost directly behind the sun, and Mars over here. As a reminder, everything in this direction here is the morning sky, everything in this direction here is the evening sky. So we basically still have Mars in the evening sky, Venus in the morning sky at the moment. So if we now zoom out to the outer solar system, you can see that the outer planets are in a much more favorable position for viewing at the moment. We have Saturn over here, so as seen from the Earth, definitely in the evening sky. Jupiter is still a bit in the morning sky at the moment, but as we'll see, because the Earth is moving in this direction, we will see that Jupiter is now rising earlier every night. Uranus and Neptune also kind of in the same direction there as Saturn. So zooming back in and then having a look at where the planets are moving over the next couple of months, we will see that Venus is basically disappearing behind the sun from our point of view. So that's its superior conjunction with the sun. And we can see that Mars is also pretty much behind the sun from our point of view over the next couple of months. So not much to see there. So we'll fast forward this until mid-January, where we can see that basically the Earth is overtaking the sun here. We will be able to see Mars again in the early morning sky, but it'll take a few months for that to come back. Outer solar system in mid-January, we see that Saturn is now moving closer to the sun from our point of view. So that means that Saturn would set earlier, same as Neptune, while Jupiter will be in opposition, which means that it's exactly opposite the sun from the Earth, and that's the best time to view it. So let's look at the all-sky view on the 1st of December. So this is from our top pad at MPAS. So Mars is really too close to the sun to observe. It's heading for conjunction on the 9th of January. So you can see it very close to the sun there in this view. Sunset is around 8:30 p.m. now. The summer solstice, our longest day of the year, on the 22nd of December. Looking at the moon, we have the November new moon on the 20th, then the full moon on the 5th of December, the December new moon on the 20th of December, and then again a full moon on the 3rd of January and a new moon on the 19th of January. Looking at some of the outer planets, Saturn, we can see, well, this is around close to 9 p.m. We see Saturn very high in the sky and very close to Neptune. So those two will stay very close to each other for a while. We also see Uranus here now rising pretty early and it's now past opposition. Saturn will head for its eastern quadrature on the 17th of December, which means that it forms a 90-degree angle between Saturn, the Sun, and the Earth. So that's an interesting illumination where usually you can see the planet cast a nice shadow on its rings. It's just that at the moment the rings are still very much edge on, so we won't be able to see much of that at the moment. Right, fast forward to around 10 p.m. And looking at the main stars in the sky, we can see Fomalhaut, Achernar, and Canopus, still the most prominent stars in the evening sky here, forming this line here. But we can see that Betelgeuse, Rigel, Sirius, and Aldebaran are now joining them in the east from around 10 p.m. Right, so these are clearly summer stars that are coming into view nicely now. Looking at the constellations around 10 p.m., we can see the Southern Cross down here very low in the sky. So that's typical for this time of the year. And Scorpius is setting very early in the west now. And Orion is making its return to the evening sky. So from around 10 p.m. we already have Orion well above the horizon. And that's a clear sign that we're returning to summer. Okay, moving on towards the end of the night, we can see Jupiter now rising a bit earlier, around midnight at the moment, and it's heading for its opposition on the 10th of January. So this is a great time to observe Jupiter. It's very bright, very large, and yeah, the best time to observe near its opposition. Otherwise, not much going on here. So we can see that sunrise is now around 10 to 6 in the morning. Venus is an early morning object, but it is heading for superior conjunction in early 2026. So not visible for a couple of months because it's too close to the sun. And Mercury also stays very close to the horizon in the morning sky, but a bit further away from the sun, so still observable. Quick view at the apparent sizes of the planets on the 1st of December. So you can see Jupiter now really dominating this. It's very, very large in the sky as it's heading for opposition. And you can see that Saturn is still very much edge on. So we can only see basically a line through the planet, which is just the shadow that the rings are casting on the planet. But this will open up again over the next few months. But of course also Saturn will set a bit earlier every month from now. Mars really heading away from us, but also invisible behind the sun from our point of view, but it's getting really tiny now. Comets. We have two comets that might be interesting. We have C2025R2 Swan still in the sky, but now around magnitude 11, so probably not that easy to image. The more interesting one, around the same magnitude really, but interesting because it's an interstellar object, is 3I Atlas. I'm sure you've heard things about it in the news. It's still not an alien spaceship. It's still not doing anything out of the ordinary. It's just a comet that's coming from outside the solar system and passing through at a very high speed. It's now rising around 3:30 a.m. That's for December the 1st. So there's now a few hours before sunrise where it may be observable. And we've seen the first images come through from amateur observers taking images of 3I Atlas now. So just to give you an idea what that orbit looks like, or it's not an orbit, what that trajectory looks like at the moment. So you can see here, this is for the 1st of October, when it was very close to Mars. And the Earth was around here, so it was observable from Earth. But we can see in the animation now how it's actually heading through the solar system. You can see it passes by Mars and then is basically disappearing behind the sun. That was in mid-October, not visible from Earth. But as we can see, as we're heading into November, it's now reappearing from behind the sun as the Earth passes around the sun and the comet as well. And so towards the end of November, it's now well in the evening sky. And as we're heading into December, it'll rise earlier and earlier. but also it's further away from the sun, so it will be much fainter than before. So around now, around the start of December, might be the best opportunity to image. So on the next slide, I just have a little animation that shows you where on the horizon, over the horizon, it will be at around 3:30 a.m. So this is on the 24th of November, starting there right on the horizon, really. So keep an eye on that cross here. That's where the comet will be. So when we head further into December, you can see that at 3:30 a.m. it will be a bit higher above the horizon every night. So from around mid-December, it's actually well above the horizon and should be observable through largish telescopes. Okay, and finally, meteor showers. We have the Geminids, probably the best meteor shower of the year, between the 4th and the 17th of December, peaking around the 14th. These often produce bright, medium-speed meteors, and there could be up to 50 an hour. There's a bit of interference from the moon after midnight around the peak, but it's still, it's not around the full moon, so it might still be okay to observe. We also have the Leonids, which are smaller, less prolific shower from the 6th of November till the 30th, peaking on the 18th, so we're already past the peak for that one. All right, that's all for Sky for the month. The sources, as always, were Stellarium, NASA Eyes on the Solar System, and for the last time, the Astronomy 2025 yearbook. And unfortunately, there won't be a new yearbook for next year, so I'll have to find a new source for all the important data for next year. And I'll see you in January.
This is in the nature of a bit of historical astronomy photography or astronomical photography around the 1980s, where you only had film available. This PowerPoint was made specifically for physics students and for photography students, a combination of both. Basically, there are 4 types of astronomical photography: untracked camera, tracked camera, focal plane, eyepiece projection, and video. Let's look at the untracked camera first. You set the camera up at full aperture, hold the camera steady on a tripod with the lens cap on, and the purpose of that is to get rid of any vibration that might occur. Lock the shutter open, gently remove the lens cap and leave it off for about 10 minutes. Replace the lens cap, close the shutter. That was the basic idea. And you ended up with star trails. That, incidentally, is the 5-inch refractor at Ballarat. You may recognise the dome, people who've been there. These are the sorts of star trails that you got by doing that sort of thing. That one actually is in colour. And, of course, you could add your own patterns to that to identify, what stars you were actually following. In 1999, some of these are later than the 80s, you had a Leonid in 1999. Anyone who got up for the Leonids on Tuesday? You wouldn't have seen a damn thing because it was cloudy. Another Leonid, 2001, another one, 2001, and one in 2001 again. These are all taken in central Victoria. South in Victoria was always cloudy, so it was nothing new the other night. Auroras, again, time just by opening the shutter and leaving it open for a while. And I can't remember the name of those satellites, but they were very, very bright for a few seconds.
Iridiums.
That's right. And again, these all show up nicely. There's 2 of them side by side there. One occurred earlier than the other one. And the second lot is a track camera. In other words, you put the camera on some tracking device. This is the device that I've still got and still use. It's a time switch out of a SEC hot water system switch. And all it does is track the camera around and off you go. You've got to point it at the pole, of course. You've got the axis there. Plus or minus 1 degree, you can get away with for about 10 minutes. After that, you get tracking error. That's the technique for finding the pole, as you probably are aware of. Settings: camera on full aperture, shutter held open, exposures 10 minutes may start to show tracking error. Now, one of the problems with doing this sort of thing is a problem with film called reciprocity failure. And what that means is that if you expose for, say, 10 seconds, you will have to expose for another 2 or 3 minutes before you start getting the same sorts of results. In other words, the film ceases to be able to record information. A little bit of a nuisance when it comes to that sort of thing. You may recognise Scorpio there, part of Scorpio, blow it up. That's all done with that single camera just on a 24-hour clock. Again, Scorpio. Longer exposures give you Scorpio there. You may recognise Antares down at the right-hand side, and then to the left of there is the cluster M4. Where are we? I've lost myself now. Anybody recognise that? Is it Orion? Yes, it says Orion. Yeah, I was just trying to recognise exactly. The Orion Nebula being shown there. Again, you've got an aircraft going across there during the exposure. International Space Station. You'll notice that I've wobbled the camera as I've opened the shutter, and then the same when I've closed the shutter. Hence you've got the little wobbly line. International Space Station. This was in central Victoria in 2001 during the Leonids. All of these were taken using the tracking device. You'll recognise the small magellanic cloud, and the left-hand star is 1987A, the supernova. So you get those sorts of things coming up quite nicely. 97A again. And of course you get comets. There's Comet Austin, 1990. Bennett, 1970. Halley, and another one of Halley. The interesting thing about Halley was that if you looked at it in the evening, it was just a blob. If you looked at it in the early morning as it was coming in, you got the tail. Most people only saw the blob because they didn't realise that. These are various other comets, again, taken but using the same technique on a 24-hour clock. Linear A2. Now...
Sorry, John?
Go ahead.
But how long were those exposures with the comets?
Probably about 10 minutes. Something like that, because you start getting errors in the tracking after that, because you've only set it up by eye. This is the thing. All right, a little bit of light theory. If you've got a point light source, then you get diverging rays coming from it, which means you don't get an image. So in other words, the light that's coming from these lights here is diverging, and therefore you don't get an image on film of it, unless of course you have a lens on the camera. Right, light coming from a distant object is collimated. That means the light rays coming from it are parallel. Our eyes are able to perceive collimated light, but if we get too close to what we're looking at, it's diverging, and therefore we can't focus on it. So we can focus on stars easily. We can focus up to something like 10 inches or something like that. Anything inside that is no good because it's not collimated. So if you've got a distant object, such as a star, the light coming from that obviously is coming from a long distance and is collimated. you need a lens to get an image onto film, onto your CCD, or indeed anything else that you want to project it onto. Right, image size depends only on the focal length of the lens. So in other words, if you have a long focal length lens, you'll get a bigger image. So if you're taking a photograph of the moon, for instance, if you want a large image of the moon, you've got to have a long focal length. This is just incidentally using a single lens. There's no eyepiece, no nothing. Just a single lens, or indeed a single mirror. Image brightness depends on focal ratio, which is the focal length divided by the lens or mirror diameter. That gives you the f-stop. Same thing applies to camera lenses. Nothing new there. So if we've got a focal length of say 1,200 millimetres, diameter 150 millimetres, then we get an f-stop of, wait for it, f8. The diameter of the moon image in this case would be about 1 centimetre. So you get a 1 centimetre image on the film. Yes, we're talking about the business of non-collimated light coming to the eye. Image is too close, object is too close, so therefore obviously you're not going to be able to focus on it. The eye can only focus on light that is nearly collimated. I'm repeating myself there. Collimated light comes from a distant star, so you can look at the stars with your eyes completely relaxed because the light's coming in collimated. The light that comes to an eyepiece or from an eyepiece is collimated, so your eye can focus on it, but you've got to adjust it so that the light coming out of the eyepiece is indeed collimated. If you want to produce an image on film, you don't want it collimated, you want it to come to a focal point and therefore produce an image on the film. So therefore the film has to be in a different place than your eye. So you've got to move it outwards in order to be able to do that. If you move that inwards, it would then eventually become collimated and therefore you could look at it directly. Right, focal plane photography. This is where you only have the main lens, you don't have an eyepiece involved. The lens is removed. This is an old Spotmatic F, which I incidentally still own, a film camera still, and you can place that at the focal plane of the objective lens of your telescope or mirror, and you're able to look through the viewfinder of the camera and be able to focus it properly. Hence the telescope main lens only, no eyepiece. This is the best way to get a clear image because the more optics you put in, the more errors you get. For focusing the object, you can read that. Right, you need some sort of guide scope. This was a colleague of mine, a bloke by the name of Doug Scott, and this is the 5-inch telescope at Ballarat again. He's looking through the finder. You'll see the camera there on the right, showing how you do that. He's got his fingers on the shutter release, and the clock, which is driven by the weights, is tracking. He can adjust it as he goes just to make sure that it's still staying in the centre on the crosshairs. And hence the sorts of photographs you take of the moon, one of Jupiter near the moon, all of these were taken at the focal plane of the telescope. And indeed an eclipse of the moon. Next one is eyepiece projection, where you put the eyepiece in and therefore you get the image on the film directly. The eyepiece is moved outwards a little so the light rays are convergent. so that you can get an image. Oh, that's the old 5-inch again at Ballarat. If you've been to Ballarat at all, that's the one that's in the dome there. I haven't been there for years. But the idea is that you focus through the back of the camera. These are the sorts of images we were getting on film. With those with a bit of imagination, realise that's probably Jupiter and Saturn. Pretty crude stuff. And Venus. A guide scope is needed for long exposures. And hence a cluster, I think that one's M7 from what I remember. You recognise that one?
Toolbox?
Yep. Various, there's Jupiter disappearing behind the moon. It's when it comes in front of the moon you've really got to worry. And of course eclipses. Solar photography. Best way to look at a solar eclipse is to find a tree, because all the light that's coming through the tree will no longer be blobs but little crescents. So you can actually observe the eclipse by just simply looking at the light coming through the tree. These are the telescopes that I'm just trying to think where it was. It was one of the schools I was at, and you can see they had a couple of 4-inch telescopes there that they projected the image of the eclipse onto a piece of paper. So you can project it using any telescopes you like. The main thing is not to look through the eyepiece. But it's a good way of looking for sunspots as well. When I originally started an interest in astronomy when I was about 13, I had a pair of binoculars and I used to sketch the sunspots on the image that was projected from the binoculars for about 3 metres away. It worked. Bit fiddly. Right, solar photography, you can use a device called a Herschel's wedge. Now the way this works is that most of the light goes straight through, most of the light and heat goes straight through, and some of it is reflected at right angles from the front surface. Now if you put a normal bit of glass in there that wasn't a wedge, you'd get an image from the front of it and the back of it almost superimposed, not quite superimposed. So you'd have a double image. Now by putting it at an angle like that, the image that's coming from the back is shot off in the wrong direction so that it doesn't go out into the camera. Now that was originally devised by, old William Herschel, was it? I think it was William Herschel, otherwise referred to as Willie, I suppose. But anyway, that's what the Herschel's wedge is. And there is an example of a Herschel's wedge being used again on that 5-inch telescope. I have my own one as well. There's your 99% going out the back. By the way, when you're using one of these, you mustn't put your hand in behind the Herschel's wedge, because you're at the focal, you're quite close to the focal point of the objective, and you can burn your fingers. A lot of energy goes out the back. And hence, these are the sorts of shots that you'd get using that technique. This incidentally, I think that one was, I'm not sure whether that was with the wedge, it might have been slightly different, but hence you could take photographs of eclipses. Oh, we'll go back one, sorry. Mercury going over the face of the sun, that occurred on the 10th of the 11th, 73. I don't know where the next one is offhand, but nevertheless, they occur, I think every something like 20 years, and then there's a sort of another one 4 years later, and then another 20 years. I can't remember exactly what the figures are, but that's the sort of thing. And then another photograph of the same thing, of Mercury going across the face of the sun. Mercury just a little chip out the side. And that's
from the same event, John? Or
sorry?
Was that all from the same
Yes.
event?
Yes. That's a photograph off Dramana Pier, just to show you what you can do with the telescope. I got an ex-student of mine to go race out on the end of the pier and sit there specifically for the purpose. And finally, video. We didn't have CCD cameras at that stage, but we did have these little video cameras. And by putting those onto the end of a telescope, you could make images on those. You can get an impression of the size of the device. I've got a few of them still at home somewhere, but these are the sorts of photographs you were taking with them, and as you can see, they're not very special. One of the things I have got is a Herschel's wedge. Now, if you go to your local car wrecker, you can get a rear vision mirror, one of the internal rear vision mirrors out of a car. And those, in fact, are a wedge. Here's one that's a broken one. Fair enough? And if you scrape the silver off the back of them, when I find the right one, you end up with this sort of thing, which is a wedge of glass. All you have to do is scrape the silver off the back, and you can mount that. I haven't actually made one from this particular one. I got part way through it and then got waylaid for some reason. But as I say, all you have to do is to get one of the internal rear. You know the ones in the middle of the car where you flick it in order to get rid of the reflection coming from the car behind you? That's because it's a wedge. You're getting a reflection from the back and the front of the wedge. Then you use a welding filter to cut the light down even more. This is an arc welding filter. You make a circle on that and you can use that as a filter. The downside is that your images are all green, but of course you can play around with that in your computer anyway. I think that's about it. Any questions? As I say, it's a historic view. It wasn't intended to be something that is worth tackling these days, but nevertheless it gives you some history into the way in which we were playing around with it.
How long were the solar exposures?
Sorry?
How long were the solar exposures?
Solar, they would have been probably 60th of a second. But the biggest problem with long exposures with stars is this reciprocity failure. In other words, if you wanted to improve an image, you make, say, a 4-second exposure of the stars, but if you want to improve on that image, you've got to do 20 minutes because the film doesn't record the light consistently. It's any photographer here would know about reciprocity failure because the same thing happens when you're taking photographs of people and so on, when you do long exposures. What was the other one?
Were you using black and white or colour?
Some of those were colour, as was reasonably obvious, but most of the time black and white. Tri-X and HP5.
And developing yourself, were you? Or
Sorry?
were you developing the film yourself? Or
Well, yes, I processed the film.
Yeah.
Oh, yes. I did a bit of push processing where you actually increase the effective speed of the film by developing it for different times. Okay.
Well, good. All right. Thanks, John.
No worries.
Tonight's video is about the meaning of space-time, given by Juan Maldacena from the Institute for Advanced Study in Princeton. So this is not part of Princeton University. This is a completely separate, standalone, independent institute from the university. This public lecture was given at the Perimeter Institute in Canada a couple of years ago, and hosted by Dr. Sabrina Pasterski from the Perimeter Institute as well.
I'm very happy to have the honor to introduce tonight's speaker. Juan Maldacena is one of the giants of the strings community and theoretical physics more generally. His proposal of the ADS-CFT correspondence was a groundbreaking discovery that has served as a catalyst for countless research endeavors over the past 25 years, attempting to understand the deep connections between gravity and quantum field theory. Born in Argentina, Professor Maldacena received his PhD from Princeton University and is currently the Carl P. Feinberg Professor at the Institute for Advanced Study. He's a member of the American Physical Society, the American Academy of Arts and Sciences, and the World Academy of Sciences. He's received many awards throughout his distinguished career, including being one of the inaugural laureates of the prestigious Breakthrough Prize in Fundamental Physics in 2012. Tonight, he will discuss ideas that arose from the study of quantum aspects of black holes, and will also delve into how wormholes are related to quantum entanglement. Join me in welcoming Juan Maldacena to the stage.
Thank you very much. Okay, thank you very much for the very kind introduction. It's a real pleasure to be here. I've had a wonderful week during the Strings Conference, and I'll try to transmit some of the enthusiasm that we string theorists have, for our field. So I'll be talking about the meaning of spacetime, black holes, wormholes, and quantum entanglement. Okay, get this. So Galileo said that the book of nature is written in the language of mathematics and geometry. So let's talk a bit about geometry. Don't worry, I will not talk to you about mathematics. So we'll talk about geometry. Let's start with Euclidean geometry. So it's based on very simple concepts such as points, lines, mainly straight lines, circles, etc. And out of these concepts, we can use it to do many things. For example, we could use it to describe images. In fact, many software programs use this type of geometrical concepts to store the images and so on. This is just an example. Now, geometry arose from technological necessities of the time, like measuring fields, levying taxes, etc. The Greeks formalized and abstracted the rules of geometry, and they summarized them starting from some axioms. And they had a list of axioms, so Euclid had a list of axioms, and one of them was, for example, just to give you an example, that if you give 2 points, any 2 distinct points, then there is a unique line, unique straight line passing through them. Okay? That's, I guess, something we all think it's obvious. That's a starting point, and if you assume this, then you can prove many other things. Now, this process of formalizing geometry, these geometrical constructions, has continued to this day. And in fact, now we can imagine curved geometries and higher dimensional geometries and so on. And we have similar principles to describe all of these cases. Now, geometry is a very basic notion. It is possible even to find it in unexpected places. And so I'm going to give you an example of how we can find it even in children's games. So there is this game called Spotted that has many different cards with different images. And when you play, you have to match an image that is in your card to the image that's been played, to the image in a card that's been played. And by the way, I'm not getting any ad money. So, for example, these are the cards, and for example, you have these 2 different cards, and then you can find the image that is in common between these 2 cards. Can you find it? Yeah, there it is. So, for example, between these 2 other cards, there is also an image in common. Can you find it? Okay, good. You're getting good. Okay, so we are not going to continue. So what we see is that given any 2 cards, there is a unique image in common. Now, there is a kind of geometry behind this game. So I just said that given any 2 different cards, there is a unique image in common. And this sounds similar to that postulate of geometry if we replace the word cards by points and image by lines. So we can, from this little game and this little system of cards, we can abstract this notion of geometry. And in fact, so we define replacing the names in this way. There is a geometry behind this game. In fact, something called finite geometry, which is something that was developed in the 17th and 18th centuries. There is also higher dimensional geometry behind language models such as ChatGPT and, well, a lot of software programs. For example, in that case, words are represented as points in some higher dimensional space. That's another example. Now, these concepts of geometry were used to measure the geometry of our real world, the Earth. So Eratosthenes developed this simple observation where he noticed that if you have a vertical stick at some time of the year, it has no shadow, but if you move some distance away, it will have some shadow. And then by measuring this angle and this distance, he could estimate the size of the Earth. In particular, he showed that the surface of the Earth is not flat, but it's a curved space, it's curved geometry. So this shows, for example, that Euclidean geometry was wrong for measuring fields. So you have to use a different geometry, the geometry of a sphere. Of course, it's that little mistake that you make is small for small fields. It only gets big if you were to measure fields which are the size of a continent. So the notion of Euclidean geometry continues to be good for relatively small objects, such as small fields. But it's one of the first examples where we go from this flat geometry to the curved geometry. Now, still at the time and till the beginning of the 20th century, it was believed that Euclidean geometry was a good description for describing the three-dimensional geometry of, let's say, outer space, or the space in which the Earth sits. Okay, now let's make a small break from geometry and go back to physics. There is an important physics principle from the beginning of the 20th century, which is the principle of special relativity. The principle of relativity itself is older. It goes back to the days of Galileo, and it says that observers moving with constant relative velocity observe the same laws of physics. So if you are in a moving cart and someone is in a stationary cart, they both make the same observations. Now, special relativity has one extra postulate which says that the speed of light is the maximal speed of propagation of signals, and also it's the same for all observers. So all observers measure the same speed of light. So this is an additional law of physics, and in accordance to the first postulate, it's the same for all of them. So this is a little graph, and here we have the red observer is stationary, sees the light traveling at a certain speed, and then we have the moving observer, and your intuition would say that what speed would he measure? Would he measure the lower speed or the same speed? Lower, exactly. That's what your intuition would say. But the idea in physics, in reality, this person actually sees exactly the same speed. And the only way this can work is if time flows differently for the two observers. So the two observers have a different notion of time, and that's a consequence of this principle of special relativity. So what this implies is that we can join space and time into a new kind of geometry. So we can play a game somewhat similar to the game we were playing, this children's game we were discussing. We were going to discuss a new kind of geometry where we are going to define a point in a slightly different way. So we're going to define a point as an event, something that happens at some place in time. So for example, a point would be the beginning of the lecture that happened here in this room. Okay? And we can draw that, for example, if space was just one-dimensional, we have this is the direction of space, and for us sitting still, this would be the direction of time. And then after a while, at the end of the lecture, we'll have another event, which will be the end of the lecture. That's this other point. And so those are 2 points. Now, lines will be trajectories of particles or observers. So for example, if you are sitting in your chair, you are not moving anywhere, so you are sitting, hopefully, during the whole lecture. Hopefully, you won't leave during the middle of the lecture. Then we can have a particle, let's say a neutrino, that came from the sun and went through us and crossed us at the beginning of the lecture. By the end of the lecture, it will be that neutrino will be very far away. Okay? We can have one that is traveling a little faster. And finally, we can have a light ray which travels as fast as possible. and that's the maximal propagation. So any straight line of an observer moving with constant velocity will be within that. Well, we'll have it to travel within this range if it's traveling, let's say, to the right. Now, so the light ray goes at the maximal velocity. Now, something interesting is that this, so if we are the static observer, we divide space and time according to this, let's say, axis. So this is space and this is time. If we are a moving observer, like, let's say, this one, we would call our time direction. So we are just sitting here. For us, as we move forwards in time and not moving in space, that would correspond to, let's say, this axis. That's this axis. An axis of equal time would correspond to, actually, it turns out to correspond to a line like this. So what they call space and time, each of these observers, how they divide space and time, depends on the velocity they are moving at, but they are all seeing the same, let's say, combined space-time. So the conclusion is that out of space and time, we can make a geometry in the way that we just mentioned, and that's the geometry used to describe physics in accordance to the principles of relativity. Now, we'll make a small apparent detour from geometry, and we'll talk about the force of gravity. So the force of gravity, you probably remember from your high school days. So you have two bodies, let's say a big mass and a little body, small mass. And the force of gravity says that the acceleration that this mass feels is, first of all, independent of this mass and proportional to the other mass and the distance and the Newton constant. Now, there are two things I want to draw your attention to, is that the acceleration of this mass, so how this mass will move, is actually independent of its mass. The second aspect is that the force is instantaneous, so that it only depends on where these masses are. So, for example, if I were to move this mass if I suddenly move this mass, immediately this other mass will feel the force changing. Now, this is bad for relativity, so the Newton's law has to be changed so as to make it consistent with the principle that no information can travel faster than the speed of light. However, this first fact will be something that will be retained. In fact, that observation is something that Einstein called his happiest thought. And this is the idea that if you are falling freely in a gravitational field, your weight disappears. So in other words, the main effect of gravity disappears. So for example, if you are sitting in an elevator, you are standing in an elevator on top of, let's say, a scale, you will see your weight. But then if the wires break and you are falling freely, then you're falling at the same rate as the elevator and the scale and so on, and your scale will show 0 weight. Okay? Weight has disappeared. Now, I don't recommend doing this experiment in an elevator, but I'm told that it's very, very fun to do this experiment in outer space. I haven't done it myself. But the astronaut and the spaceship are both falling in the gravitational field of the Earth, orbiting the Earth, and both moving in exactly the same way, and they feel the astronauts feel they are floating. Okay, so based on that observation, Einstein developed the idea of general relativity, and general relativity is Einstein's theory of gravity. And the basic concept, the basic idea, is that the geometry of space-time is not flat, but is curved. And the idea is that if you are a particle moving freely, falling freely, that particle will move along that space-time along the shortest trajectory. So the analog of a straight line is the, in some sense, shortest trajectory. And then he had the idea that this curvature is produced by the presence of matter. So he had an equation which basically says that the curvature of space-time is proportional to the amount of matter that you have. So our conclusion is that so space-time is really described by this curved geometry. And again, as we said before, points are events, and straight lines are the trajectories of observers falling freely. And for our everyday experience, of course, that space-time is pretty close to flat space. Now, in some cases, you can really see very clearly the curvature of space-time. So this is an example where we are here at the Earth, and we are looking back at the universe, and this is called gravitational lensing. So here we have a cluster of galaxies, which is just a big mass that curves the space-time geometry, and then the light ray that comes from a galaxy that is even further away will follow the lines of, let's say, straight lines. And here we see that we have two straight lines that initially are moving apart from each other, and then they meet again. So that's something that could not happen in flat space, where two lines that are initially moving away from each other would continue moving away from each other. But here, they come back to the Earth, and in the Earth, we see two images of the same galaxy. So a very clear demonstration of the curvature of space-time. And it is somewhat, in some sense, similar in spirit to how Eratosthenes showed that the curvature of the Earth that the Earth was not flat by looking at the trajectories or the properties of light rays. Now, this theory makes one interesting prediction, which is the existence of gravity waves, which was detected a few years ago, and where researchers here at the Perimeter played and made interesting contributions to this discovery. Now, in addition, there were two very surprising predictions, black holes and the expansion of the universe. And I call them very surprising because Einstein himself didn't quite believe these predictions. So when people started talking about these things, he was so surprised. He said, "No, this can't be. You must be doing something wrong." In fact, there is this famous phrase, "Your math is great, but your physics is dismal." This is what Einstein told Lemaitre. And I like this phrase very much because that's sometimes what other physicists tell us string theorists. Now, we now have great observational evidence for both. We have this picture of a close-up of the black hole at the center of the Milky Way that I'm sure you've seen. Black hole is roughly there. And this is taken by the Event Horizon Telescope. And again, researchers who work here at the Institute participate in this wonderful experiment. And we also have a lot of evidence of the expanding universe. I'm sure you've seen this picture. I won't explain it in detail. Only just to mention that we have a lot of evidence from the cosmic microwave background, of course, the whole history of the formation of galaxies and so on. And now we'll turn to a new topic. We'll make a slight change, and then we'll try to go back to gravity. And the new topic is the other revolution of the early 20th century, which was the development of quantum mechanics. So classical physics was changed in two ways. One was the development of special relativity, the relativity of time, and the discovery of space-time. And then the idea of the curved space-time or general relativity. And now we're going to discuss, say, a few words about quantum mechanics. I'm sure you've heard something about quantum mechanics before. And quantum mechanics is a new type of description of physical systems that the main point is that it is intrinsically probabilistic. So things are not completely determined, but there is a certain probabilistic element. And then there are a few other properties of quantum mechanics, such as the uncertainty principle. There are some things you cannot know at the same time, like the position and momentum of a particle. And also there are other features, such as the so-called sum over paths, that sometimes if a particle can go either through one slit or another slit, there is a sense in which the particle goes through both slits, and then there is some interference effect, similar to a wave, for the probability of finding the particle at this point. Okay, but what's important, something that's important for us is that quantum mechanics explains many things. It explains chemistry, it explains atoms, it explains matter, etc. Now, it's a pretty weird explanation of matter, where atoms are mostly empty space. So the size of the nucleus is much, much smaller than the size of the atom. And in fact, it required a lot of work to explain simple, obvious things. So there are some things that we take for granted, but in this quantum mechanical description of atoms and matter are actually very interesting. In fact, the physical appearance of most substances are what we call emergent properties. So if we say, well, why is the screen white? And why is, it's because of how it reflects the light, and perhaps we have my computer is shiny, so why is the computer shiny? Well, it has to do with particular properties of the arrangements of many atoms. And so they arise from a large number of quantum particles and their interactions, so many of these properties. So, for example, a mountain can appear very solid. Also, the water can appear very solid to the insect. The water would not appear solid to us. And in fact, the mountain also would not appear solid if you were a neutrino or a dark matter particle that can just pass through the whole mountain without interacting with anything. So in both cases, the mountain or the water consists mostly of empty space, and these solid properties that we take for granted come out of the interactions between these different particles. Now, so that's an important concept, this idea of emergence. And now we'll introduce yet another concept. So in the history of the 20th century, people put together the idea of quantum mechanics with the idea of special relativity, so the idea that signals can propagate at most with the speed of light, and this led to the modern description of particle physics, which is called quantum field theory. So that's you could call it relativistic quantum mechanics. It describes the behavior of elementary particles, the interactions between elementary particles. So in this description, each light, for example, is described in terms of the quantum of light, which is a kind of particle, and it can be exchanged between charged particles, and that leads to the attraction between the charged particles. And in the same way that we can describe pictures using geometrical concepts, we can describe the evolution of particles in our universe by a set of lines that there are geometrical concepts which exist in space-time. So now this picture here is in space-time, and there are particles and their interactions. And this type of diagrams represent, so that they can represent the propagation of these particles, and there is a way to calculate the probabilities for each of these diagrams. So quantum mechanics is probabilistic. And so there are formulas behind these pictures, which we can use to describe particle collisions, and it agrees very well with what we see in particle collisions. Okay, and in this way we can describe all the matter we see at the very fundamental level. We describe with this type of pictures. So particles moving in the space-time geometry. Now, there is an important question, which is whether we can include gravity. Can we finish the developments of the 20th century and put together general relativity with quantum mechanics? So we know nature is just one. It's not divided into gravity and electromagnetism or matter. This is just a division in our mind. Nature is just one. And we should have a way to describe quantum gravity, but we should have a consistent way of discussing general relativity together with quantum mechanics. Now, there are two approaches to this problem, and one is an approximate approach, which is similar to the quantum field theory approach, and it's an approach, as I'll review, works well for some problems, but not for others. And then there is a more precise approach, and is what we would call a full quantum theory of gravity. And I will start with the approximate approach. So in the approximate approach, the idea is very similar to the idea that one had for ordinary particle physics. We would just now have all these particles moving, instead of them moving in a flat geometry, they are moving in a curved space-time geometry. And again, you can create particles, and you have to add one particle, which is the graviton, the quantum of gravity. And in this way, you can describe various things. And when the radius of the curvature of the universe is very much larger than the so-called Planck distance, this works very well. And in particular, so let me just say what the Planck distance is. So Planck distance is a combination of the various fundamental constants of nature, G Newton, H bar, and C. So these are basic constants, and out of them we can make a quantity which has dimensions of length. And Planck made this combination when he discovered the Planck constant. And he said this distance must play an important role in physics. It's a very, very tiny distance, so it's not a distance we can see with a microscope. In fact, our best microscopes today can explore a distance of order 10 to the minus 18 meters, so a distance much, much bigger than 10 to the minus 35 meters. Just to give you an idea of the size of the Planck scale, let's imagine that we grow to the size of the galaxy. Okay? Now we are the size of the galaxy. The minimal size we can see today with our accelerators would be our size. Okay? So it's a big difference. The Planck scale would be the minimal size we can measure today with accelerators, so another factor of 10 to the 18. Anyway, this is a very tiny distance, but it was recognized as a basic length scale of general relativity. And it's basically the length scale at which the quantum effects of gravity become very important. So if you were to look at space-time at this very tiny distance, space-time would be highly fluctuating and so on. Would be very probabilistic. Space-time at long distances is very, very sharp and clearly defined, very classical. So this approximation, this simple approximation to quantum gravity is good enough for most circumstances of daily life. In fact, it's also good enough for almost all places in our universe. Now, there is a situation where there is a complete failure of this approximate description, and this happens at two places. So the most interesting one where it happens is at the beginning of the Big Bang. So at this very first instance, we think the curvature of space-time became very large. And the word singularity means, if you don't know what it means, you get the right meaning, because we don't know what happens there. So you know, just means we don't have any idea of what happens there, and according at least to this theory. And the other case is singularity. There are similar singularities in the interior of black holes, as I'll explain in a little while in more detail. So these are places where the approximate theory fails. So it fails in these extreme circumstances. And this circumstance here is, of course, very important for us, because that we would like to understand what happens there. We would like to understand the beginning of the universe. Okay. So that's the main motivation to study quantum gravity, is to understand what happened at the beginning. So for that, we need a full theory of quantum gravity, the full theory. But before we start talking about the full theory, let me continue. We'll come back to the full theory later, but let me discuss some important successes of the approximate approach. So now we go back, take a step back again, and we'll discuss in more detail some important successes of that approximate approach. So the first one is that it leads to a big surprise for black holes. And this is the fact discovered by Hawking that made Hawking very famous. The idea that black holes, the laws of quantum mechanics in the context of black holes, implies that black holes can emit thermal radiation. They emit some radiation. And this radiation is such that the temperature of the radiation increases as the black hole size decreases. So if you have a smaller black hole, it will look hotter. It would be like hot, let's say, it could become red. And if it shrinks enough, it could even become white. So it could be so hot that it could have the temperature of the sun, and it would look white to our eyes. So it would be a white black hole. It looks like a contradiction in terms, right? Black holes were supposed to be black, but now they're black, they're white. So big surprise. Now, this effect is almost irrelevant for astrophysical black holes. With astrophysical black holes, well, they're completely irrelevant for astrophysical black holes, because astrophysical black holes are very massive. They have very low temperature, so low that it's even lower than the temperature of the cosmic microwave background, so you have no hope of seeing this tiny temperature for astrophysical black holes. If you had smaller black holes, the effect can become bigger. For example, a black hole of the mass of a continent would have the size of the bacterium, the size of the wavelength of typical wavelength of white light, and then that black hole would really look white. Okay? Now, this type of black holes are not readily made in our universe, but in theory, this is what you would find. Now, let me just explain why that effect happens. So I'll explain it with some kind of cartoons. And the basic point is that the quantum vacuum is a somewhat complicated state. So the quantum vacuum is such that if you looked at the small region of the vacuum, what you measure is quite unpredictable. So you have so the measurements at that point could change from measurement to measurement, and there is a kind of lack of information that you have if you only look at the little portion of the vacuum. And this is a computer simulation for a particular quantum field theory. The whole vacuum is simpler. So if you look at the whole vacuum, then you see, for example, that you have no particles. If you look at the small portion of the vacuum and you look there, it might be that you see something like a particle. But if you look at the whole vacuum, you don't. And the reason is essentially that you have some ignorance in some parts, but that ignorance is correlated with some other ignorance you have in the other part. If you look only at the other part, but if you look at the whole, you have a complete picture which produces a more predictable and precise state. Now, this might have looked a little abstract, so since it was a bit abstract, let me just describe it with an analogy, because it's an important point for the rest of the lecture. And imagine that somebody tells you a portion of a sentence. So let's say Mary stepped out of her, and then you can decide how to complete the sentence. Any volunteer to complete the sentence? Want to complete the sentence? What? Good, so that's one possibility. Okay, so you can complete, and we'll all perhaps come with different ways of completing this sentence. And so we have a certain lack of information of what the sentence is. There are many possibilities for what lies outside the sentence. So we cannot say what the sentence means. It doesn't have a definite meaning, definite, clear, crisp meaning. Now, we know it involves Mary, but we don't know the full meaning. It could end in different ways. But if someone told you the full sentence, let's say Mary stepped out of her comfort zone by explaining quantum physics to a group of investors, then you have the full meaning. Now it's clear what the whole thing is. So if you have the whole picture, clear meaning. If you have only a small picture, so that's similar to looking at the portion of the vacuum versus the full vacuum. Okay, so in that case, you get a well-formed sentence. You have a portion, we lack some information. And in fact, there is a way to quantify the information we lack. So in the case of the sentence, we could imagine listing all the possible ways to complete it. Some will be very improbable, some will be more probable. And we can quantify, there is a well-defined way to quantify the entropy or the lack of information that we have. Using so-called information theory, we can assign a number to, roughly speaking, counting the number of different ways in which it can end. So I said the vacuum is then in this analogy like a well-formed sentence. So now let's return back to black holes. And so this is a picture of the space-time geometry around the black hole. Remember, roughly time is roughly like this, and space is roughly like horizontally. Exactly what you call space and time depend on how you are moving, but roughly speaking is that. So each point here is an event that happens in a space-time. Light rays are moving at 45 degrees. And this region here is the outside of the black hole. And if you are here, is the region that looks like flat space far away. So if you have a light ray that is coming out, it will go out like this. So here, this direction, you can think of it as the direction that comes out of the black hole. So, and then there is, if you are at some event here and you shoot a light ray going outwards, that light ray will go up, but then eventually it will collapse into a singularity. So we have here a singularity in the future. So this is a bit like a big crunch. So the interior of a black hole looks like a big crunch geometry where the universe collapses at some finite time. So if you're traveling here as an observer, you find that your universe collapses and you die when you get to the singularity. So I'm sorry, that's what general relativity says. Okay, so and not only do you die, but there is no way to escape from this according to general relativity. What was the question? Yeah, that's right. You can't escape because that would require you to travel faster than the speed of light. So the speed of light moves here at 45 degrees. If you wanted to escape, you would have indeed to travel faster than the speed of light. Absolutely correct. Okay, so that's the space-time geometry. And there is a particular light ray, which is the one that divides the region from which you can escape from the region where you, sorry, the region where you can escape, which is this one outside, from the region where you cannot escape. And we call that the horizon. So this is some light ray. And so if you are an outside observer, you can see only a portion of the geometry, so the portion that is outside, because the points here, the events that are inside, can never send you a signal. So you ignore what happened here in the interior. You can only measure what happens here in the exterior. So we had the vacuum of space-time, the whole space-time vacuum, and it's split by the horizon into two pieces, the piece outside and some piece inside. And so we have a phenomenon similar to what we had with the sentence, in the sentence analogy, where we get only a portion. And because we get this portion, it leads to some ignorance, some randomness. And in physics, this ignorance or randomness translates into temperature. So whenever we have something at finite temperature, we have this feature. And the quantification of this lack of information is sometimes called entropy or disorder, is what the lack of information of what's inside. Now, from the black hole, we can calculate this entropy or amount of disorder using the laws of thermodynamics. So Hawking gave us the formula for the temperature of the black hole as a function of its mass or its energy. And then we use the laws of thermodynamics, and we can get an entropy. And it turns out that the entropy has a very simple formula, which is just the area of this horizon. So this is like a sphere. It's the trajectory of those light rays. And it's the area, so the area has some dimensions of length, and divided by that Planck length, the same quantity that Planck had originally thought that it might play an important role, here indeed plays an important role and appears in this formula. Of course, since this distance is very tiny, for if you have a macroscopic area, this is a huge, huge, huge entropy. In fact, if you were to calculate the entropy of the universe, most of the entropy of the universe comes from the entropy of the big black holes at the center of galaxies. That is more important than any other entropy. And then the second law of thermodynamics would imply that the area should increase. And indeed, the laws of general relativity say that the area always increases. So Hawking had shown, even before this formula was developed, that if you have a horizon, the area of the horizon always increases. That this just comes from solving Einstein's equations, those equations that we discussed before, that have nothing to do with thermodynamics. So it's an interesting consistency picture. Okay, so black holes emit radiation, they lose mass. We call that evaporation. Now this, as I said, was irrelevant for an astrophysical black hole. But let's imagine someone let's say someone came and had some way of making a very small black hole, let's say a 1 kilogram black hole. And so someone gives you this 1 kilogram black hole, and you would say, well, 1 kilogram black hole cannot attract me very much. It's probably not a big problem. Okay. However, due to this effect, the 1 kilogram black hole, using the formula E equal to mc squared, will evaporate and will emit an energy which is equal to its mass. And that energy, if you work out what it is just like a 20 megaton nuclear bomb. So don't accept the 1 kilogram black hole from anyone. Fortunately, there are not such black holes around. And we have described some results for black holes from this approximate method. Remember, all these results are derived by this approximate quantization method for gravity. But there are some questions about black holes which we cannot answer using this approximate method. So for example, what precisely comes out of a black hole? So if you throw in some matter into a black hole, you can throw water, or you can throw, I don't know, gold, and what comes out seems to be just radiation. Can we recover the information of the matter that formed the black hole? And in other words, is this process of black hole formation and evaporation consistent with the laws of quantum mechanics, which says that this information cannot be destroyed? Now, to answer this type of questions, we need the full theory. So now we'll return to the discussion of the full theory. And we really don't have a full theory, but we have a theory under construction, which we call string theory. And now we are having this conference on string theory. And the goal of this conference is to make progress in the construction of this theory, understanding this theory better and extending its range of validity of the things that we understand now to understand more things about this theory. Maybe one way to say this is that our picture of the theory is something like this picture. Okay? So you can see there is a building there, and you're pretty sure there is a building, but we don't have the sharp outlines. We don't know everything about the theory. We know we have some idea about the theory. Now, my attempt today will be to try to give you an idea without formulas, without mathematics. It will be more impressionistic. Hopefully, you will get the idea that there is some picture, but that will remain to be seen. So what we're going to try to see now is that, well, I'm not going to describe this theory in detail. I'm going to discuss one aspect, which is that we're learning some interesting things about the quantum aspects of black holes. And so we'll focus on one particular aspect. And the aspect that we will focus on is the idea of space-time as an emergent concept. Now, we can motivate this as the following, let's say, question. These are the type of questions you have in the university entrance exams in the US. I don't know if you have those in Canada. But so these are questions about analogies. So water is to atoms as space-time is to. So what, you know, so we use atoms to describe water. What are the things we use to describe space-time? So space-time atoms, you would say. Are there something like this? And the idea is similar. So we'll talk about an idea that is somewhat similar. But these elementary atoms, or sometimes we call them qubits. So qubits is the basic amount of quantum information, or the basic degree of freedom in quantum mechanics. These atoms are not local in our space, but they are really sitting far away. Okay? And so this is the idea of holography. And the idea is that, so we understand this in some special cases. So some universes with a constant negative curvature. And in these universes, they have, in some sense, some boundaries, some region very far away. And in these universes, we can describe everything that is happening in the interior in terms of some qubits, some quantum degrees of freedom that live on the boundary. And these degrees of freedom are interacting a lot with each other, but they don't have any gravity. So gravity only exists in the interior. This is a kind of little picture for this. So the idea is that we have two separate descriptions, two different descriptions. One is we could have a particle moving in the interior. So in these spacetimes, there is a kind of gravitational potential well that keeps particles moving in the interior. Then you have other particles that this funny motion that is represented here tries to give you the idea that these particles are strongly interacting with each other. Now you can ask, well, how you would describe a black hole in this way? So in these spacetimes, you could imagine that you have a black hole in the interior. And the idea is the black hole would correspond to a large number of particles that are strongly interacting and live at the boundary. Okay? And the temperature and entropy of the black hole would come from the temperature and entropy of these particles that live at the boundary. So the idea of this description is that the theory on the boundary obeys the rules of quantum mechanics, and so therefore, so does the black hole in the interior. And then the black holes are consistent with quantum mechanics. But for that, you need to accept this holographic conjecture that space-time and the boundary theory are related in this way. So we'll come to the discussion of emergent geometry. So in this description, geometry is emergent in the following sense. So we have some space-time, and the qubits live far away at the boundary. But the gravitational space-time has one more dimension. So let me try to explain how that happens using an analogy. So imagine a sentence. So we come back to this idea of a sentence. And the sentence says, if a man does not keep pace with his companions, perhaps it is because he hears a different drummer. Now, when you heard this sentence, you probably in your mind divided it into various words. And then you probably group the words in some way, analyzing the grammar of the sentence and so on, and the meaning of the sentence. you found the various sub-sentences or sub-clauses and so on, and until you got the full sentence. So in fact, there were also long-distance correlations, for example, between the word man, his, and he, or between the concept of keeping pace and drummer. Okay, that's a kind of deeper level correlation. As we include more words in our analysis, we get to a deeper meaning of the sentence. Okay, so we have, in some sense, an extra dimension, which is the depth of meaning or the direction of meaning in the sentence. So how deeply encoded is a particular concept within this sentence. So in this analogy, the idea is that the state of the quantum system is analogous to a very long sentence that lives at the boundary. And the bulk geometry is doing some analysis of the meaning of this particular sentence. So that's in the analogies, reflecting the correlations that you have between the various words of the sentence, and there are correlations that are encoded that involve short distances along the sentence, and some involve words that are very far away in the sentence. And for example, particles in the spacetime could be particular words that are either repeated or have some correlated meaning in the sentence. And a bulk observer, so someone who lives in this bulk, is a bit like a character in a novel whose text is living at the boundary. Okay, so someone who lives in this space-time, that's what it would be. He's also some kind of emergent concept or emergent object in this description. And it's interacting with other emergent concepts and so on. So perhaps a slightly more accurate way to describe this is that the boundary is a superposition of many possible sentences. That has to do with the quantum mechanical aspect that involves probabilities, and the bulk spacetime represents those statistical correlations. Now, you can ask, what is a black hole in the spacetime? So let's make an analogy for that. So we go back to the sentence, and now we change some words. So here we change the word his to its, and he to she, and so on, and we change these words. And once we change this word, we lose the full meaning of the sentence, of the original sentence. We keep somehow a little bit some of the meaning, but not we lose the meaning at a certain depth. So beyond that depth, we have a kind of horizon. We don't know what this speaker is talking about. Okay? And then if we continue changing words, then this horizon of meaning gets closer to the individual words, and the sentence makes less sense. Okay? And that growth of ignorance has to do with it's represented in the bulk as the area growth. Okay? And we could imagine the situation where we completely change all the letters in the sentence. Now the black hole grows as much as it can grow, and we just don't know we don't know anything. There is no information in this sentence, apparently. And now imagine that the changes in the sentence came from a reversible process. So for example, an encryption algorithm. So in that case, it is possible to reverse the process and recover the original sentence. So that the laws of physics at the boundary change the state at the boundary, similar to changing the sentence, and it's analogous to an encryption process in the sense that it is reversible. And so we can, in principle, undo the formation of the black hole and recover the information. So that's what it would mean to recover the information. Okay, now let me go back and discuss again this idea of portions of a sentence. So if I show you again this sentence, Mary, little lamb, you might have different guesses for what the block word might mean. So there is one that probably you first thought about, but there could be many other ones. So Mary sold a little lamb, Mary killed a little lamb. Okay, that would be a cruel Mary, but maybe she was hungry, I don't know. So you're missing part of the meaning. And so in the same way, we can consider this very long sentence that lives at the boundary, or this very long, very complex quantum state that lives at the boundary, and block off a portion. So you decide not to look at that portion. And when you do not look at that portion, you have some ignorance, and there is an interesting formula characterizing the ignorance that you have, in this case of the quantum systems that give rise to geometry. And this formula says that the ignorance that you have is proportional to the area of a minimal area surface. So you consider a surface that ends at the tips of the region you blocked, and you can let it move, so it can be anywhere, but you find the surface that has the maximal area. And we're in a curved geometry, so if we were in a flat geometry, the surface with the minimal area, would be a straight line. But in the curved geometry, in this particular curved geometry, the minimal area is this surface, so that's the one that has least number of angels and demons, and you can calculate this minimal area. And you divide by L Planck, the Planck length in the interior, and that gives you the entropy. So it's very similar to the formula for black hole entropy, except that we are not talking about the horizon, we are talking about this minimal area. And this is a very important was a very important formula because it related a geometric concept like area to a quantum information concept as this entropy, or amount of information of a blocked region. Now, we can also ask whether we can recover a portion of the bulk if we miss, what we can recover about the bulk if we miss a portion of the boundary. And then the idea is that if you're missing this portion of the boundary, you will miss also this portion of the bulk space-time. In other words, when you have a very long sentence and you're missing this region, you could imagine that you can recover meaning, or the meaning of the sentence, or let's say it's a novel that is in the regions very far away from, let's say, the pages you lost, but there will be some part that you would certainly not know. And depending on the structure of the novel, you might or might not figure out what's going on, but you certainly will miss something. And so the part of the meaning of the novel that you missed would be this region inside. So that's the analogy. So this idea that the bulk is encoded in the boundary is encoded in a boundary in a way that also similar to how quantum information can be stored in a quantum computer. So in order to remove errors in quantum computers, you store information also in some kind of distributed way, where information is encoded in correlations between different degrees of freedom. And that's called a quantum error correcting code that was developed in the 90s by Peter Shor, and is how quantum computers are supposed to work. And Almeridon and Harlow found more recently that actually we should think about the emergence of space-time using this type of ideas. So all these developments have shown that space-time emerges in some way from quantum entanglement, or in other words, that space-time emerges from correlations in this quantum system. Or another way of saying this is that geometry is related to patterns of entanglements or correlations. So it's somehow similar to how meaning emerges from the correlations between words when we have sentences. So in fact, people use ways to describe, so I'm not going to explain this picture, but this picture appears in papers of tensor networks. And so this is some way to encode quantum correlations in a system. So, and Guilford Vidal was one of the developers of these ideas. He was here at the Perimeter Institute, and I think he recently left and worked in artificial intelligence. So he went from the quantum world to the world of sentences. But what you can see is that the pictures are kind of a similar structure. So this analogy is actually conceptually, well, it's kind of vague, but it has some sense. Now, let me make a comment. So this idea that the space-time can be emergent from quantum degrees of freedom implies in principle that you could make a little quantum, if you have a quantum system and you can manipulate it as much as you wish, then you could make a little tiny small universe that is governed by Einstein's equations. So just to make the tiniest universe we can imagine that is governed by Einstein's equations, we would need about 10,000 qubits. Okay? So quantum computers today have about 50, 100. So there is some way to go. But, well, maybe we'll get there sometime. In contrast, our big universe, the universe we live in, we think we would need of order 10 to the 120 qubits. And in addition, our universe is expanding, and we don't really know how to describe it using these methods. So now I'm going to discuss an interesting case of the relationship between entanglement and geometry. It's a little more dramatic case of how geometry can emerge from entanglement. And this is just going back to a funny feature of the simplest black hole solution. And it is the fact that the simplest solution of vacuum Einstein equations describes actually two black holes. So these are two black holes that are very far away, but they are sharing a single interior. So in some sense, there is a geometry which at some moment in time looks a bit like this. So they are far away, so this is the far away distance, but they are really connected through the interior. Now, the interior is time dependent, so the distance between the two through the interior changes. And let's say at time equal to 0 is like this, and then as time progresses, it becomes thinner and more distant in such a way that if you were a traveler trying to go from one side to the other, you wouldn't be able to go. You will fall into the black hole. You will get crashed at the black hole singularity, and you will not be able to traverse this wormhole. But the space-time that it describes has these connections. And the interpretation is that this geometry corresponds to two entangled black holes. So each black hole has some entropy, some degrees of freedom, some qubits. That if you look at one of them, they are thermal, they have some randomness. But if you look at two of them together, that randomness is correlated in such a way as to make a pure coherent whole. And that pure coherent whole gives rise to a geometry which is connected through the interior. So let me give you another analogy for this connection through the interior. So let's imagine we have two sentences. So we have the same sentence we had before, and now we have the same sentence here in the bottom. It's the same sentence, but in Spanish. Okay? And so if you analyze these sentences, the words are quite different. So the grouping of letters is different. But if you start analyzing it, you get to a point where the two sentences have the same common meaning. So you would have this region of the geometry is doing the analysis of the English sentence, and this region of the geometry is giving the analysis of the Spanish sentence. And at some point, you get to the meaning of the sentence, which is common to both cases. So this is a bit like analogous to that wormhole. So they have this common meaning. Now, there's a small variation of this process where you bring the two black holes closer together, and you allow some simple form of interaction between them. And in that case, then the wormhole can become traversable. In that case, you can indeed travel between one side. So first of all, the black hole ceases to be a black hole. There is no horizon anymore. And then you can go through this wormhole. I won't explain all the details. But in quantum mechanics, this process of allowing some interaction and then you going through the wormhole is related to quantum teleportation. So let me, what time am I supposed to end? Okay, well, a few more minutes. So some analogy for this business of quantum teleportation through a wormhole. So this process has three elements: entanglement, communication, and this idea of wormhole. So let me just make a little bit some classical analogy. So imagine that Bob and Alice had been married for many years. So they share many common memories. Okay? So that means that Alice can send Bob, let's say, a look or just simply a few words, and Bob will know what she means. Okay? So in some sense, there was an idea, which is a much more complex thing. Well, an idea that got transferred from Alice's mind. This is kind of representation of her mind with all the meaning and so on inside, and Bob's mind. So the idea went from Alice to Bob, and it managed to go thanks to the fact that they shared all these common memories and just some simple look. So if a person from the outside that only hears the word or saw the look would not be able to guess what the idea was because they don't have their common experience. Now, I'm not talking about this, but there was a recent mini revolution in our field about similar wormholes that were important for understanding how information is encoded in Hawking radiation and the black hole interior. So I won't discuss that. So in conclusions, I emphasize the fact that quantum systems can give rise to a geometry this emergent geometry, and that the geometry of our own space-time could be emergent in a similar way. We really understand this for universes that are a bit different from ours, that have, let's say, mostly negative curvature. Our universe is a bit different because it has positive curvature. Now, an interesting consequence is that we could make these little tiny universes in the laboratory, very, very tiny. And in the future, we hope that this will lead to an understanding of the singularity inside of black holes. We don't have that yet. And after understanding that singularity inside the black holes, which has to do with the Big Crunch, hopefully we'll then understand the singularity at the beginning of the universe, which is really the biggest question in our field and the thing that really drives us forward to keep investigating this theory further to understand how the universe really began. And with that begin, we just end. Thank you.
Thank you so much, Professor Maldacena, for your fascinating talk. We will now open the floor to questions. So for those here in person, there's a microphone set up in the stairs to the audience's right. We'll ask that you limit yourself to just one question relevant to the talk, just to ensure that everyone has a chance to ask their question. So please form a line here. We have someone already. Please go ahead.
Thank you, Professor, for your whirlwind tour of the recent developments in quantum mechanics. I have one 10-part question. No, but so as a string theorist, you're obviously partial to unification of quantum mechanics and general relativity, unification based on string theory. But what are other leading candidates for unification of these two understandings that are not based on string theory?
Yes. Well, I mean, the question is the idea that quantum mechanics and quantum mechanics and general relativity should be put together is very old. People had various approaches. String theory, I think, is the one that is further along. But there are ideas, for example, of triangulating your space-time and then integrating over all, or summing over all possible ways of doing that, defining a quantum theory in that way. There is something called loop quantum gravity. There are various other ideas that capture some aspects of this story. But I would say that if you want to get to the point where you really derive Einstein's equations and a continuum geometry, just to string theory is the only one that can do that.
Hi, thank you for the talk, Professor. So my question is, in approximate theory, you mentioned that entropy is proportional to the area. But if entropy is increasing, shouldn't the size of black hole should keep on increasing and not evaporate?
Very good question. Yeah, very good question. So the entropy is equal to the area in the classical theory. So actually, when you do this approximate approach, the entropy gets an additional term, which is the entropy of the quantum fields that live outside the geometry. And so the full entropy of the system outside is the area plus the entropy of the fields outside. Now, when the black hole evaporates, the black hole becomes smaller, the area becomes smaller, but there is Hawking radiation. And because Hawking radiation is thermal, the entropy outside has also increased. And in fact, it increases more than the decrease of the area, so that the total entropy actually increases. This is something that was proven by Aaron Wall in about a decade ago. So it's relatively recent. Yeah, sure.
No one knows how to make a black hole, it was said in the meeting here, 2020, February. But 20 years before, in Scientific American, it more or less had the same argument. You described traversable wormholes, and the warp drive is sort of a transformation of that. In Illusion of Gravity, which you didn't mention, they just turned on the RHIC, and you said at the end, it was too soon to tell, but it may be generating tiny black holes from the ADS correspondence. Do you still think that in the more recent Scientific American, they described sort of the low viscosity, but they attributed it to the strong force. But the strong force is made of gluons, and you also mentioned gluons. Do you think you could, in the fifth dimension, as he described, generate some sort of chain reaction to create this bubble? What are your thoughts?
Okay, well, your question contained various different elements. Let me see if I can say. Well, first of all, before the LHC turned on, people discussed that perhaps it could make black holes. The LHC has turned on and has not produced any black holes, as far as we have seen. That was possible in some scenarios. So that's one point, at least not four-dimensional black holes. You can, I wasn't, yeah, other parts of your question refer to the type of quantum system that has known gravity descriptions. And there is one example of a quantum system that involves particles similar to gluons, so similar to the particles that govern strong interactions in nature. It's a theory which is, let's say, a cousin of the theory that describes strong interactions, so it has gluons and also some other particles that we don't have in nature. But when you put all those particles together, they give rise to this 5 extra dimensional space-time. And in that description, when you have a collision of these particles, you can make a black hole in the 5th dimension, so in the extra dimensional space. From the point of view of the boundary theory, that black hole is viewed as a gas of particles similar to what we had in one of the transparencies, where we had the particles moving at the boundary. So it's described as a ball of gluons, or a quark-gluon plasma, it's called. And so this correspondence, that this relationship, can then be used to calculate, or as a toy model for trying to understand that those processes in QCD. So I'm not saying QCD is the theory of strong interactions. So for the theory of strong interactions in nature, we don't know what this 5-dimensional description would be. But for similar theories, we do know. And for those, they can be used as a toy model. Thank
you. Would we be able to harness Hawking radiation or any other energy from a black hole?
Yeah, that's a good question. So if we look at the black holes that we have in nature that are known to exist, no, because they are, first of all, they are very far away, and they emit very little Hawking radiation. There is more matter falling into the black hole than there is radiation coming out for those black holes that exist in nature. Now, if you ask me what's theoretically possible, right? The best possibility is to have magnetically charged black holes. So if you had, I told you that black holes that have 1 kilogram would explode like a nuclear bomb. Now, if you had a magnetically charged black hole, so that's very difficult to make. We think they can exist theoretically, but they would be super difficult to make. But if you could make them, well, if they existed for some reason, then those would emit Hawking radiation and would settle into a kind of black hole at 0 temperature that's not emitting Hawking radiation. Then you can take some matter and drop it into this black hole, and that matter that you are dropping in would almost instantly be converted in Hawking radiation and would be a source of energy. So that's one scenario you could have. It's very science fiction-like, very unlikely to be realized for many reasons. In particular because we don't think nature naturally produces these magnetically charged black holes, and making them artificially seems exceedingly difficult.
You talk on the view that time here had a beginning, so I was wondering what your thoughts are on these theories if time didn't have a beginning, like if
Yes. Yeah, we draw this picture with something that somehow starts here, and what you're asking is, could there be something before this point, some other universe? Time existed before the Big Bang, and then something happens here. And, well, we don't know. Maybe we could have it, maybe we cannot have it. But the point is that we don't understand, until we understand what happens here, we cannot really know for sure. So people sometimes say, oh, perhaps there existed. I mean, there are some people who speculate and say, well, maybe there was a time before the Big Bang, and then they make some theory of what will happen, but that's not really a well-defined theory. It's one of these theories where you say, well, something existed before, then a miracle happens here, and then, we don't have a well-defined theory that allows us to go from before to after. And part of the question of understanding what happens here is to be able to answer that, your question, which is a very good question.
Thank you so much, Professor Maldacena. That's all the time that we have tonight for Q&A. So I want to thank everyone for joining us, both here at Perimeter and online. And let's all thank Professor Maldacena again for his wonderful lecture.
Hello, it's Scott Manley here. Today I want to talk to you about artificial gravity. Artificial gravity is of course a staple of science fiction, partly because if you're shooting a TV show or movie, it makes shooting scenes on Earth a whole lot easier. But in the early days of spaceflight, there were lots of concerns about the human body's reaction to zero-G, to the point that Yuri Gagarin would have to input a 3-digit code to unlock the controls on Vostok 1, just in case being in zero-G made him space crazy. While the first decade of human spaceflight showed that humans could easily adapt to zero-G for short missions, there were many reasons to think that for longer missions, say on space stations, it would be a good idea to have access to artificial gravity capabilities for the sake of the long-term health of the crew. Specifically, it was known, even with a week or so of exposure, that the human body will slowly lose muscle and bone mass in the absence of gravity. On the engineering side of things, the laws of physics give us 3 ways to generate gravity-style forces for a crew. But only one of these is actually viable for spaceflight: rotational artificial gravity. You see, gravity is a phenomenally weak phenomenon, and while science fiction loves artificial gravity generators in the floors of spacecraft, again because it makes it easy to shoot and because it lets you design cool spaceships, there's nothing in the laws of physics that would imply or suggest that this is possible. The only way that we know right now to generate a gravity field is with a huge amount of mass, such as a planet. Planet-sized chunks of mass are great for living on, but they're kind of inconvenient to carry along if you're doing spaceflight. Now, another way to do this is linear acceleration, where you're going faster in a straight line. And that does indeed generate the perception of gravity. Indeed, Einstein built general relativity by assuming that accelerating in a straight line and planetary gravity should be identical and no experiment can tell them apart. And guess what? That works pretty well. Now, spaceflight is great for generating linear accelerations, but you only get a few minutes during launch and re-entry. Those chemical rocket engines can deliver the G-forces you need, but only for minutes before their propellant is depleted. In TV shows like The Expanse, the spacecraft use fusion drives that can accelerate for days on end without running out of propellant. But that's a technology that is driven by the needs of the plot, and it may never be possible with human technology. Also, the magnetic boots that we see in the show are again really nice if you're trying to shoot a TV show, but they really just provide a way to secure your feet to a surface without actually providing the gravity loads that make the human body work out and decondition. So rotational gravity is what's left, right? That's the only one that's possible. And indeed, the idea of large rotating space stations was around for decades before anybody ever flew in space. But a lifetime later, and we still don't see rotating space stations, although there are many people who would love to build one, such as the Voyager space station. So, a quick reminder of the math that this involves. If you have an object that is moving in a circle, you need a force pushing it inwards towards the middle, and that force has to be proportional to the mass, the radius of the circle, multiplied by the angular velocity squared. And in physics, we measure angular velocity in radians per second. So there's 2 pi radians in a complete circle in 360 degrees. So now if you want to generate an Earth-like 9.8 meters per second of gravity with a 10 meter radius structure, that's about 30 feet, then you need to rotate it at about 1 radian per second, or about 9.5 RPM. If you make the radius longer, then the rotation rate gets smaller, and if you reduce the gravity that you want, then similarly you can use lower rotation rates. Now at this point, I should put on my physics tutor hat and explain the difference between centripetal and centrifugal forces. For an object to move in a circle, it has to have that centripetal force pushing it towards the center of rotation. But if you are a person in a rotating space station with walls and you can't see out, this force to you appears as the ground plate pushing up against you. You feel a centrifugal force pulling you down towards the floor, and that feels like gravity. But this is different, equal and opposite. Look, it's different enough that it can serve as a limitless source of pedantry from physicists. So anyway, this kind of construction is of course used in training pilots and astronauts. You have the centrifuge facility. This is to give pilots high experience in high G loads on the ground. You'll put them in a test cabin or a test car, spin it around at high speeds and generate the G forces that they need to learn to handle, to make sure that the body is capable, that the G suit works properly, and just to teach them adaptation techniques to moments when they're dealing with this. But this kind of training is something that lasts for hours rather than the weeks or months that astronauts might experience on a space station. So, this kind of rotational facility is well understood by the spaceflight community, and that meant that it was also known that there were side effects from spinning humans around like this. I mean, it's honestly something we learn as kids, right? You get very dizzy if you spin around too fast, and turning those childish understanding and perceptions of dizziness and falling over into quantifiable research on human physiology is a serious endeavor that requires lots of effort, resources, and dealing with people being sick. So there's 2 main effects that we see when humans operate in a rotating environment. Firstly, your body uses the semicircular canals near your ears to detect rotation, and that helps you keep your balance. And they do this by detecting the motion of fluid in these sort of circular cavities. And this responds to the rotation of your head. Now, if you're sitting perfectly still, your brain will take that as a non-moving reference frame, and you'll stop getting dizzy even if you're rotating. But if you're turning your head, then you expect a certain rotation. If the room is turning and you turn your head, you will get a different rotation, and that will confuse your brain, and is a great way to give yourself motion sickness. One of the first things that people learn to do in rotational experiments is to stop moving their head to minimize this effect. And the other thing is, in a rotating environment, any motion through that will frequently require forces that are different from the same motion in a non-rotating environment. These are broadly described as the Coriolis forces, which at planetary scales affect the atmospheric motions and help make tropical storms that rotate counterclockwise north of the equator and clockwise in the south. But at high rotation rates, simply reaching out your hand to pick up something might result in the fictional Coriolis force pushing your arm away from the path that your brain has planned for. Your brain is working with its previous experience and all your motor functions to balance this out. So when this happens, your motor control system needs to relearn how to perform these basic tasks. And you can learn a specific motion really quickly, minutes even. But then, in some rotational environments, if you turn to face a different direction or move your hand in a different direction, the Coriolis force will again be different, and you need further adaptation. It takes days to become fully adapted to a rotating environment. So one question that scientists wanted to answer was, what kind of rotation rates can the human body handle for long durations? Long enough to get over that initial sickness, long enough that the gravity would be needed to avoid deconditioning of the body. Can people perform at the same levels as they do in a non-rotating environment? Or is there some penalty that can't be eliminated by training at any rotation rate? Is there an upper limit on the rotating conditions that human can handle? Because that in turn, if you've got a limit on your rotation rates, that will set the minimum radius for a spacecraft that is using rotational artificial gravity. Now, one of the problems with all the studies like this is that they're interested in hypothetical rotating structures in space, but they have to take place on Earth, and you can't subtract Earth's gravity because we don't have anti-gravity. So one type of test is the rotating room, where a room is rotated around its vertical axis like this. And you might actually have seen this on YouTube. There's a video with Tom Scott that does this. But these have been around for a long time. The US Naval Medical Research Laboratory built the slow rotating room facility in 1958. That was like 10 meters across, and they had living quarters in there for long duration testing. So people would live in there for weeks on end. At 1 RPM, people could operate with very little adaptation, but most subjects would begin to suffer motion sickness initially when the room was spinning at about 3 RPM. Again, turning your head was the thing that would really trip off motion sickness. But from that, people could adapt as you spun the room faster and faster, and they could learn to handle much higher rotation rates, even up to 10 RPM, although quite a few people couldn't adapt and ended up making frequent use of the sick bags. Yeah. Now, in the Soviet Union, again, they did similar experiments using rotating rooms, and they came to the same conclusions. But the rotating room isn't the same as a spacecraft rotating to provide artificial gravity, because the axis of rotation is in a spacecraft is parallel to the floor, but you can't do that on Earth because of the ever-present gravity of the Earth. However, there have been tests on large centrifuges with whole living spaces at the end, with a rotation rate fast enough to incline the floor to provide a non-sloping surface for the occupants. And this means not only is the space rotating, but you're also dealing with stronger gravity. So you had better be sure that you are not going to fall over, because if you fall over due to your lack of balance, you're going to hit the ground a lot harder in these environments. So this footage here is from a Soviet experiment where, again, people would live for about a week at a time. And one of the more amusing demonstrations is the arrow throwing, where they curve around thanks to the Coriolis force. Although the elevator system is also another interesting thing, because you want to bring out the doctor to the crew to study them. But moving radial is really hard because your gravity forces and everything are rapidly changing as you move down this arm. And it's one of the more disorienting experiences. NASA also had a very large centrifuge system. It's called the Rotating Test Facility, and it was built by Rockwell out in California. So on one side, there was this living area. It was like 40 feet long by 10 feet wide. It was actually a section of an aircraft, apparently. And people would live in this for about a week at a time. The other side, they counterbalanced this by having the walking wall. And this was a vertical wall, and they had straps to support people so they could actually stand sideways on this and test walking like prograde or counter rotation, right? They could also use this same support harness system to simulate ascending and descending ladders, because again, that's another thing that was quite complicated for your body to learn. But the only experiment I've seen that's really flown in space and provided artificial gravity is the Soviet Bion 3 or Cosmos 782 mission. So that had a small centrifuge on board it, and they had plants and animals in containers at different distances from the rotation axis, and that allowed them to compare different simulated gravitational environments. And as far as I can tell, this is the most significant test of artificial gravity ever flown in space. It's also notable as the first time a US experiment flew on a Soviet space mission. The spacecraft was actually based on the Zenit design, which was a Soviet photo reconnaissance satellite that shared a lot in common with Vostok, because back in the 50s and 60s when Sergei Korolev was developing this, he realized he could get money from the people that wanted a human spacecraft and from the people who wanted a spy satellite and build them one spacecraft, right? So yeah, all of this stuff went on for decades, and huge reports that were compiled for all these experiments. And what they all basically say is, slower is better, but rotational artificial gravity is possible in structures that are comparable to the size of the International Space Station. There would be a few engineering problems to solve to make sure like the thing remained balanced and you have proper seals and transitions, but there's nothing insurmountable there. Instead, we don't see rotating space stations because there's no real selling point, since the same intense medical research has helped develop ways to stave off the deconditioning associated with zero-G through consistent exercise to make up for the body not supporting your weight doing mundane things in zero-G. The ISS is primarily concerned with zero-G research, and that kind of research is hard to do in a rotating station. You would need a non-rotating section. But the ISS does miss out on the ability to perform experiments at lower gravity levels than those on Earth. I mean, at one point there was a centrifuge facility planned for the ISS, very similar to that found in the Bion 3 satellite. And that would allow small biological payloads to be exposed for lower gravity for long periods of time. But ultimately this was cut to make the space station more affordable. But with the new wave of space tourism, there's suddenly a number of people who are interested in going into space and may find the idea of staying in space for a while, taking in the views, and who don't need experiments that are in carefully controlled microgravity. So maybe the idea of a rotating space station will finally return. In the movie 2001: A Space Odyssey, the rotating space station 5 at the start, the interiors, we get to see lounges, restaurants, and a hotel. It's not a science facility. So maybe the only thing Arthur C. Clarke got wrong was the date. I'm Scott Manley. Fly safe.
Mars, once a warm, watery world with a thick atmosphere. Now, a cold, arid landscape with its atmosphere thinned out. What caused this transformation? Over billions of years, a relentless flow of particles from the sun, the solar wind, has slowly stripped away the Martian atmosphere, causing surface water to evaporate. But how exactly did this happen, and how could it affect future Mars explorers? NASA's new ESCAPADE mission aims to find out. The Escape and Plasma Acceleration and Dynamics Explorers mission is studying the planet's real-time response to the solar wind, helping us understand Mars's climate history using 2 spacecraft in orbit for the first time.
Past missions that we've sent to Mars to understand the interaction of the solar wind with the planet have only been single spacecraft missions. So ESCAPADE gives us what you might call a stereo perspective, 2 different vantage points simultaneously. This will allow us to really make measurements we've never made before and to characterize the system in a way we couldn't characterize it before.
ESCAPADE's twin spacecraft fly in 2 different formations to see how Mars responds to the solar wind in both time and space.
This is the first time that 2 or more spacecraft have worked out a formation in orbit about another planet, in this case Mars.
In the first formation, nicknamed the String of Pearls, the 2 spacecraft chase each other in nearly identical, highly elongated orbits. This allows ESCAPADE to observe rapid changes in the Martian atmosphere caused by sudden variations in the solar wind.
When we have 2 spacecraft crossing those regions in quick succession, we can monitor how those regions vary on timescales as short as 2 minutes up to 30 minutes, before we had to wait for 4, 5, 6, 7, 8 hours.
In the second formation, the spacecraft have different orbits that are more separated from each other, allowing ESCAPADE to study both the solar wind and the upper atmosphere of Mars simultaneously for the very first time.
We'll have 1 spacecraft in the solar wind so we can measure what's coming in, and then 1 spacecraft closer to Mars. This will help us understand the cause and effect of what's happening when space weather comes to Mars.
ESCAPADE will not only fill gaps in the story of how Mars's atmosphere changed, it will also help us prepare to send human explorers to the Red Planet. For example, ESCAPADE will give scientists more details about Mars's ionosphere, a part of the upper atmosphere that future astronauts will rely on to send radio and navigation signals around the planet.
Understanding how that ionosphere varies will be a really important part of understanding how to correct the distortions in those radio signals that we will need to communicate with each other and to navigate on Mars.
ESCAPADE's work could also help keep future Mars explorers safe.
Atmospheres can provide a shield that protect humans and other assets on the surface from things like solar radiation or intergalactic radiation. So it's important for us to understand how the atmosphere is changing in order for us to know what we have to do to protect humans and other assets we might put on the surface.
In addition to new science, ESCAPADE is pioneering a new way to reach Mars. Previously, spacecraft launching to the Red Planet had to wait years for Earth and Mars to line up. However, ESCAPADE is launching into a unique orbit that loops around a region in space known as L2, roughly 1 million miles away. Then, it'll return and use Earth's gravity to slingshot itself to Mars. This allows ESCAPADE to launch early and wait in space until the two planets are in the right positions. This first-of-its-kind orbit will also make ESCAPADE the only spacecraft to ever pass through a distant part of Earth's magnetotail, before beginning its 10-month cruise to Mars and starting its cutting-edge work there.
NASA's heliophysics fleet is looking at the sun's influence, and with ESCAPADE, we'll now have multi-point measurements at Mars, which will help us have a more comprehensive picture of what's happening throughout the solar system. We need a solar system-wide understanding of space weather in order to protect our technology and our astronauts wherever they go.
Effect through the L2 Lagrange point, so in other words an empty point in space, which is a very different way of doing it. Okay, now we'll close with the actual launch, which is on the 13th of November from Blue Origin. The New Glenn rocket that it was launched on is 98 metres tall, so in other words it's over 30 stories high, so it's quite a big rocket. It's bigger than SpaceX's Falcon 9 that they put all the Starlink satellites up into orbit on, which is only 70 metres. And it actually carries twice the payload of the Falcon 9, so it's quite a heavy lifter. But it's not quite as big as the big Starship rocket that has been launched. It's about a quarter less than that. Okay, this goes for about 2 minutes or so. And you'll actually notice that the cameras on board actually have buffering troubles. So they haven't quite got the telemetry downlink as smooth as some of the others, like SpaceX is usually pretty good these days. around, alas, we don't actually get to see it pop out of the spacecraft because its little cameras didn't pick it up going out, unfortunately.
Did you notice as the feet landed on the deck, there was a very quick flash there, like welding the thing to the deck?
Oh, was it? Oh, okay.
I don't know any more about it other than there was some sort of explosive device
Oh.
or effectively a weld to hold it stable on the desk. It doesn't top.
Interesting, interesting.
It has to be very quick, of course, under the circumstances.
Yeah, yeah, because of course the drone ship is on the water there, so it's moving around as well, and you've got this 30-story high rocket. I think they only recover the main booster stage, whereas SpaceX aims to recover the whole lot. So they basically just discarded the upper stage and the fairing and spat the two craft out on the way to Mars.
You're going to have a static charge involved in that.
I don't know.
Because the static charge on the spacecraft is going to be different than the surface of the ship. So it might have been part of what happened.
I saw a video last night and I was looking for it then, and it was just a very quick flash on them.
Pretty instantaneous, yeah, yeah. They actually had some buffering problems just as the thing was coming down the last few seconds. All of a sudden the video sort of froze and then it sort of tries to catch up afterwards. And so they haven't quite sorted that out yet, but hopefully they will.
Very successful. Watch for Jeff Bezos or Bezos versus Elon Musk down there. They're getting loggerheads now.
Oh yeah, oh yeah, oh yeah. All right, with that, I'll close the meeting and we meet again in January. So just a reminder, nothing in December here for that meeting. All right, thanks for coming and staying to listen to Space Time. Thank you.